here, I had to stop because the system told me the internet is not stable. I couldn't continue earlier. Let's continue here. We are talking about this straight line. There are infinitely many, uncountably many points on the line. Suppose the equation of the line is y equals x plus 1. Then any points, all the points on the line, their coordinates would satisfy the equation, right? For example, if this point has x coordinate -4, then the y coordinate would be -3. Because the y value must be the x value plus 1. So we have so many, uncountably many ordered number pairs. All those ordered number pairs make a set, and that set is a relation. So the conclusion here, the straight line, the graph of the straight line is a relation because it's a set of ordered number pairs. The set has infinitely many, uncountably many ordered number pairs here. Let's see another one. A parabola. A parabola is also a graph in the two-dimensional space. And we need to determine if this parabola a relation. Again, a relation is defined as a set of ordered pairs. Same idea actually. How many points do we have on the parabola? Infinitely many, uncountably many, right? Yeah, those points are ordered number pairs. They put it together, make a set. That set is a relation. So the conclusion here is the parabola is also a relation because the parabola is a set of ordered number pairs. Those ordered number pairs are points on the parabola. The two arrowheads also the two arrowheads means the parabola is extending or go up in quadrant 1 and quadrant 2. All right. So actually, any graph in a two-dimensional space is a relation. Let me repeat it. Any graph in a two-dimensional space is a relation because they are sets of ordered number pairs, maybe finite, maybe infinite. Okay, so I think we are ready to bring in the definition for a function. A function is a relation in which for each domain element, there's only one corresponding range element. So this tells us the connection between relation and a function. Let me make an analogy. This set human beings, this set women. We know women are human beings, but the human beings might not be women, could be men, right? Same idea. This bigger circle is a set of is a set of relations. All the relations. Then this set would be functions. Functions is a subset of relations. Functions are relations, but the relations might not be functions. In order for a relation to be a function, one extra condition has to be satisfied. The condition is for each domain element, we talk about what is domain, right? For each domain element, there's only one range element. For example, let's look at this relation. This relation is a set of 4 ordered pairs. The 4 ordered pairs are 0, 1, 0, -1, 1, 2, -1, 2, right? Is this relation a function or not? Let's determine. In order for a relation to be a function, for each domain element, there's only one range element make a pair with it. So we could use X to be the domain element, use Y to be the range element. So the condition in the definition of a function basically means for each X there's only one Y. For each X there's only one Y. But here, look at it here. For each X, for 0, for the same domain element 0, there are two different Y's. That means you have two ordered number pairs have the same X, different Y. That disqualifies this relation to be a function. So this relation is not a function. Okay? It means if we give the machine, remember, so we could actually describe a relation as a machine. The domain element X is the input. The range element Y is the output. So the relation here, when you give the machine input 0, you have two different outputs. By the definition of a function, this relation is not a function. But somebody might wonder, what if in a relation we have 1, 2, negative 1, 2 means for the same Y, we have two different X. Would that be something disqualify a relation to be a function? That is okay. Function could have two ordered number pairs with the same Y value, different X values. Because you can see for 1, there's only one Y value, make a pair with it, right? For 1, you only have 2. For negative 1, also there's only one domain element, range element. So in a function, so in a relation, you see two ordered number pairs with the same X, different Y, different Y, then that relation is not a function. But if you see two ordered number pairs with the same Y, different X, that is okay. That is allowed in a function. So do you see what I'm saying here? Please repeat this part to really get it. Let's talk about the notation of function. Function could be represented as an equation. For example, earlier we have this equation y equals x plus 1, right? It is an equation, but actually it is a function. Why? Because for each x, there's only one y. For each x, there's only one y. You wouldn't see for the same y, for the same x, you have two different y's. So we actually have a very convenient method to determine if a given relation a function or not, if the relation is a graph in a two-dimensional space. Earlier we have agreed any graph in a two-dimensional space is a relation. And we have a very convenient method to determine if the relation is a function or not. The method is called a vertical line test. So if you draw vertical line, if no line cross the graph more than once, like this one, no line would cross the graph more than once, right? Cross 0 times. Here, 1 time, 1 time, 0 times, 1 time. If no vertical lines would cross the graph more than once, then we say the graph passes the vertical line test and the graph is a function. This one is the same. As we mentioned earlier, y equals x plus 1 is a function, actually is a linear function. The straight line passes the vertical line test, so the straight line is a function. And what about this one? The parabola also passes the vertical line test, right? So the parabola is a function as well. Parabola actually represents the second degree polynomial function or quadratic function. And what if I draw more? If I have this function, if I have this graph, if I have this graph, or this graph, are they functions or not? Or this graph? So let's apply the vertical line test. No, right? Because this straight line, vertical straight line, pass the graph more than once, twice. It means for the same x, there are different y's. This one fails the vertical line test as well. So it is not a function, not a function, not a function, not a function, because this one, for the same x, there are 1, 2, 3, three different y's. This one, yes, okay, is increasing. I think it's a pretty straightforward vertical line test. So function could be represented as a graph, which could pass the vertical line test, could also be represented by an equation, like so. The output y is by itself on the left, and on the right we have an expression in x. X here represents all the first components. Remember, x here is a variable. It represents all the values in the domain. It's called an independent variable. And y here represents all the values in the range. It's called a dependent variable. X and y here do not play the same role. We can see that from the name of the two variables. This is independent. That is dependent. Independent means variable x could assume any value that it wants, as long as the value is in the domain. However, once the value of x is certain, the value of y would be certain as well. The value of y depends on the value of x. In this example, we could give x any numbers. If we give x 0, then y would be 0 plus 1, right? The output equals the input plus 1. The function, the equation, determines the pattern. How does variable y depends on variable x? So very important to see that. Function can also be described as a machine. Whenever you give the machine an input, the machine would produce a unique output for the input. Okay, so as the note says, there are three basic ways to represent a function. Use a data table. Did we have a data table? This is a data table, right? Yeah, this is a function. Yeah, we brought in as a relation to explain the definition for relation. But you can tell it is a function as well, because for any given domain element, for any person, there's only one eye color. I didn't see anyone has two different eye colors. I see cats, but not human beings, right? So this is a function. For any domain element, there's only one range element. For each person, there's only one eye color. So that is a table. Use a data table. Second bullet, draw a picture of a graph. So did I give you the examples of functions? They could be graphs. Number 3, write an equation or formula. That's what we talked about earlier. Like the straight line, y equals x plus 1, or y equals f of x, right? So three basic ways to represent a function. But in essence, you're going to know function is a set of ordered number pairs. A function is a set of ordered pairs in which for each domain element, there's only one range element to make a pair with it. You need to repeat that definition, that sentence over and over until it really makes sense to you, until you see that sentence every time when you see a table, when you see a graph, when you see an equation represents a function. Do you see what I'm saying? Okay, so let's see the package here. Let's give it a little bit of time to react. In the package number 1, which of the following is a mathematical representation of a function that provides detailed information but can become unwieldy? Unwieldy is like a troublesome, right? I would say D is out because the domain is one element, important element of a function. Domain cannot represent a function. Equation, graph, data table. Those three are the three basic ways to represent a function. And which one could be very detailed, however, can become unwieldy? I would say is A. Okay, for example, in our previous example, we have 4 people only. What if you have 1,000,000 people? Then you're gonna make the table very long, very lengthy. All right. Number 2, the range of a function is a set of what variables? Did I explain that before earlier? X is the independent variable. Y is the dependent variable. Independent variable X could represent any values in the domain. So X represents all the values in the domain. Y represents all the values in the range. So what should we choose here? The range of a function is the set of dependent variable values. You could also understand the range of a function is the set of all the outputs. And the domain includes all the inputs. Range includes all the outputs. Number 3, which of the following most likely describes a periodic function? Well, let me see how do I explain periodic function. The formal definition for a periodic function is there is a constant t such that for any x, this equation is satisfied. So that is a condition for a function to be a periodic function. F of x plus t equals f of x. One example that I can show you is we can see a graph. This is sine x is the most simple trigger function. So this is a function, right? You can see the function pass the vertical line test. Actually, we could actually continue the function like this way. And you can either steal a function because it would pass the vertical line test forever. So this is a periodic function. For every 2 pi, this is 0, this is 2 pi. For every 2 pi, the function it repeats itself. For every 2 pi, it repeats itself. So would that be okay for you to understand a periodic function? Well, maybe we can look at the 4 answer choices to understand what is a periodic function. Number 1, part A. So the way they represents the function is give you the ordered pairs. Then the x variable would be the first component. The dependent variable y would be the second component. Age of my computer is value. So let's consider how does the second component changes. How does the second component changes if the first component change? Age of my computer, the computer is getting older and older, right? And its value would becomes lower and lower. By common sense, the regular computer is like that, right? So do you see the cycling thing, like a recycle thing? No. So that is not a periodic function. Part B, first component is date, second component is your age. When the time passed by, your age would only increases, right? So as the time goes by, you are getting older and older. So this is a increasing function. That is a decreasing function. This is an increasing function. It's all the way go up. Yeah, I wish this is a periodic, like when you reach 40, you become 1 year older again, right? And you become immortal. But not that case. Your age is gonna be increasing until you die. So this is not a periodic function. Part C, first component is date, second component is number of days until Friday. Well, let's see the calendar here. Do I have a calendar here? When the time goes by, the number of days until Friday. What day today? Today is Sunday. Friday is here, right? Next Friday. Number of days until Friday. Until Friday. So until Friday, 1, 2, 3, 4, 5. 5 days, right? And tomorrow, we would have 4 days until Friday. On Tuesday, we would have 3 days until Friday. And on Wednesday, we would have 2 days until Friday. On Thursday, we would have 1 day until Friday. And on Friday, we have 0 days until Friday. On Saturday, we would have 6 days until Friday. And then we go next Sunday. We would have 5 days until Friday, right? And then 4 days until Friday, 3 days until Friday, 2 days until Friday, 1 day until Friday, 0 day until Friday. Do you see the cycle? Do you see the period? The period is 6 actually. 7. The period is 7, of course. So we have 7 days in a week. That is a periodic function. It is go back the original point and go up again. Is that understandable? Does that make any sense? Part D, Tom's age, his shoe size. I would say the function increasing. When Tom is very little, his shoe size is very small, right? When he grows up, shoe size grows up. Once he grow up, I mean like an adult, then his shoe size would remain the same, constant for a while. And maybe when he get very old, his shoe size getting down a little bit, right? That's possible. So it's not a periodic. This one is a periodic. You can try your calendar to figure that out. Let's stop here and I'm gonna continue in the next video.